Hello, and welcome back to another episode of CoffeeShop Astrophysics. For those of you who plan to be here, thank you for coming. For the rest of you, you're going to get a dose of science that you probably weren't expecting, but you can't really tune us out now because we've got the mics on. So, hope you enjoy it. Just like to point out that we also have other astronomy-focused events. Can you turn down just a little bit? Some other astronomy-focused events at the planetarium at UWM. So if you are interested in this talk and it's fun for you, you might want to check out some of their other programs and go to the planetarium website to see that stuff. Now, who are we? CoffeeShop Astrophysics is a group of grad students and postdocs at the UW Milwaukee Center for Cosmology, Gravitation, Cosmology, and Astrophysics. And we basically do these talks to get some practice talking, but also to bring the topics that we really like and love to the general public so that you can understand it a little bit. Oh, okay. If you do have an idea for the CoffeeShop Astrophysics talk sometime in the future, you can let us know. We have a sign-up sheet somewhere around here. Just talk to one of us after the show or ask a question after we finish our talk, and we'll try to include those topics in future talks. Okay, so today our talk is about neutron stars. It's the secrets of neutron stars. We want to look inside the densest stars in the universe, okay? Now, neutron stars are basically the densest object you can get outside of a black hole, and so they're kind of interesting to scientists because they straddle that line between what's possible physically for normal matter that we know, okay? And so they are very, very small. In terms of size or extent, they basically, if they were just flat and covered part of the Earth, they would only cover a large city about the size of Milwaukee or so. They wouldn't be really big. They're still very massive. They have the mass of several suns, or at least two suns around there, but they are compact, super compact, so more dense than anything we've ever seen. Because they're so compact, though, gravity actually can bend the light around them, and they're very, because they're very small, it's very hard to see them because in visible light, they're very dim, but they do give off a lot of light in other wavelengths like radio waves and X-rays, and so we are able to observe them that way better than through visible. However, Hubble is always amazing and does a lot of things. Hubble did see this little guy here about mid-90s, actually, and it is a neutron star that's about 200 light years away. Now, comparatively to the scope of our galaxy, the other side of our galaxy is about 100,000 light years, so it's a big spot, and we can only see them if they're very close. Like 200 light years is really close in galactic distance, okay? So this one happened to be really close, and so you can see it in visible light in this picture from Hubble. But with the exception of a couple that are really close, the neutron stars that are in our galaxy are too faint for us to see with visible light. So it's hard to see. It's hard for us then to measure like the diameter, the size. If we can't actually see them, we have to use other tools, and we'll talk about those later in the talk. All right, so, but basically, a neutron star is the shell of a star that already, lived its whole life, okay? And so once a star is formed, it dies. It either goes into a supernova or collapses into a remnant called a white dwarf. If it goes supernova, it can go into a black hole, or it can go into a neutron star. But we know, to get an understanding of how they form, it's better to start at the beginning. So I'm going to talk about this. This is a nebula called the Carina Nebula, and this is where stars are actually born, okay? And so gravity acts in these clouds of dust and gas in the universe, and it basically causes these clouds to collapse on themselves, okay? If the only thing that was working in these clouds was gravity, though, you would see that these clouds would just collapse directly into a black hole. But they don't. We know that they don't because you can see these jets here that form when new stars are forming. So in this cloud, basically when the density and everything starts to collapse, it gets to a density where instead of just keeping collapsing, something happens. Hydrogen basically is packed so tightly together that it can fuse into helium. And when that happens, we start getting more energy into the star, and the star basically is held up from gravity by the pressure caused by this thermal energy given off by the fusion, okay? And this is a process that we call hydrostatic equilibrium. Basically, what it says is that when a star starts to fuse hydrogen into helium, it gives off enough energy to puff the star back out and counteract gravity. And so you've got basically the gravitational pressure pushing in and the pressure from the thermal pressure from the gas pushing out, and the star becomes fairly stable. If there were too much heat, it would expand and then it would be able to radiate more heat off. And if there were not enough heat, it would contract and that would heat it up some more and then it would expand back out. So it hits this equilibrium point as long as fusion's happening where it can basically hold itself up, okay? And that's all well and good. When it does this, it basically more or less follows the ideal gas law. Now, some of you who have already had like high school chemistry probably have seen this. I learned it as PivNert, so it's one of these weird equations, and usually we don't put equations here, but in this case, I'm going to go through it. But basically, it says P times V, which is pressure times volume, is equal to the number of particles in the gas times the temperature and this weird constant R that ties all the things together. And we don't need to worry too much about what R is, but remember the volume of the sphere is dependent on its radius, okay? And so when we look in space through a telescope or anything really, we can't directly measure volume, but we can measure the radius, and we know stars are mostly spherical, so we can get from the radius, if we can measure the radius, we can say this is how big this star is, okay? Now the other thing we can do is we can sometimes get the mass, and the mass, which we can get in various ways, tells us how many particles, right? So if you know the average size of the particle and the number and the mass of it, you can guess there's how many particles there are. And so basically what this boils down to is we have density, which is the number of particles in an area of volume, and the pressure and the temperature all determine the pressure that supports, how much it can support against gravity, all right? And this is called what we call an equation of state for a star, okay? When a star is in the main part of its life fusing, basically it follows this rule, and if it's more massive, that means it's actually going to be bigger because it has more fusion going on and it's got to radiate more stuff. So more massive stars during their fusing lifetime, the more massive it is, the bigger the star is and the brighter it shines, okay? But once the fusion elements are all gone, when you can no longer get energy out of the star from fusing elements, then we have a problem. That's when the star dies. And if it's a star like our sun, you're going to get something left over called a white dwarf. Basically, when the star dies, all you're going to be left with is a core of like carbon and oxygen, and all the outer layers of the star will get blown off with solar winds, and it will be much smaller than the sun we have now, probably like half to an eighth of, or half to 3/4 of the mass that we have on the sun now, and that will be called a white dwarf. White dwarfs basically come only from stars that are about the size of the sun, up to about 8 times the size of the sun. And here we have a picture. This is actually fairly recently detected neutron or white dwarf. And this white dwarf, you can see it's an artist's conception of it right next to the moon. And the thing that's interesting about this is with white dwarfs, they actually work the opposite of the way stars that I just explained. When I said before, stars, when they're fusing, the more mass they have, the bigger they are. Well, with these, this is one of the most massive white dwarfs we've ever detected, and it's only the size of the moon. But a more modest-sized white dwarf, say like half the size of this, would actually be bigger than Earth, okay? So less mass means bigger in white dwarfs, so it's the exact opposite. So the equation of state that would govern white dwarfs, while it's a little too complicated to put up here, basically is different, and we know that because of the size differences, is different than what you would have for a normal star, okay? All right, so to understand what's going on inside these remnants, the white dwarfs, and then I'll build up to the neutron stars, I want to go back to a little atomic physics, okay? Everybody's probably seen some sort of model of an atom like this, or something with the atomic symbol where there's electrons orbiting. But basically, the basic atomic model is you've got a nucleus that it consists of some protons and neutrons. and a cloud of orbiting electrons outside, okay? But that's about as close, this is not at all an accurate picture of what's happening inside an atom, because actually electrons are nowhere near the size of a proton or a neutron. They're about 2,000 times smaller in mass, okay? So they take up much less space, or they're much smaller than the protons. And then the other part of this is to fit these electrons on, they have to shrink down their orbits immensely. You would need about 1 million of these movie screens all lined up in a square around this thing in order to actually show where the electrons should be orbiting if this were the size of the nucleus. In other words, if the nucleus of an atom were a soccer ball, the electron cloud around it would take up the whole space of Connecticut, okay? So this is just to say that most of an atom is empty space. So when you start pushing things together, instead of having a star, you can actually get things pretty cramped just by pushing atoms together, but there's still a lot of empty space there, all right? Now, in an atom, the electrons, they're one of the fundamental particles. They're called leptons, okay? But protons and neutrons are not fundamental particles. This is a little chart from CERN. It's just kind of for fun. But you can see that it gives you quarks, leptons, and bosons. Now, quarks and leptons, right, those are called fermions. And basically, quarks, you have 6 different flavors. You have up, down, charm, strange, top, and bottom, or sometimes called beauty quarks. And in this chart, the way that they've made it is you can look at the shape, and it kind of tells you what it is, but the number of eyes tells you how heavy. So as you go down this, you see they get more eyes, and they also get heavier, right? And so an electron has a bigger counterpart called a muon and a tau that are basically just negatively charged particles that have more mass, okay? And then there's also neutrinos that are leptons. Neutrinos are given off in a lot of nuclear reactions, in fission and things like that, or fusion. And basically, we see them coming from anywhere like the sun that has fusion, inside of neutron stars, a lot of different places. They basically pass right through atoms because it's so much empty space, and they have no charge at all. So right now you've got millions of neutrinos. I think it's really cool to think that, but they're just passing through your body and going in a straight line. They don't even interact, okay? So constantly they're passing through. Now, all of these are fermions, like I said, and then the other ones are bosons. Now, the fundamental boson particles are things that carry force away from, like the photon carries the electromagnetic waves or light away from stars, radiation. It also carries radio waves and X-rays and that kind of stuff, is all part of the photons regime. Gluons, they work on a smaller level. They work in the nucleus of an atom, and they hold the nucleus together. It's called the strong force, and they mediate that. These little bosons, the ZW bosons, those are for the weak force. And most recently discovered at CERN a few years ago was the Higgs boson. And that gives mass. It carries mass to particles. So basically, if you have these bosons in your particle, it'll have mass. Now, the graviton, we don't actually have proof of it yet, but it's a theoretical particle that should be there. And so I'm just kind of introducing you to these subatomic particles a little bit here. Okay, so again, I said fermions and bosons, they're 2 different classes of things. Well, now I'm going to get about as complicated as they get. This is a little bit of quantum mechanics, but you don't really need to know much about it. But basically, fermions have a property called spin, so do bosons. But the fermions, like the leptons and quarks, have a spin that's a 1/2. It's a multiple of halves if you have fermions. And for bosons, you have a spin that is a whole number, so 1, 0, etc. You can have fermions that are complex. So I mentioned the neutron and proton are not fundamental particles. They're actually a combination of 3 quarks. Okay, and we'll go into that a little more detail. But basically, because there's 3, if you have 3 things with spin 1/2, you just add those together, you get a spin 3/2, for instance. And so that's still a half spin as opposed to a whole number spin. You can also get complicated or complex bosons, which are basically combinations of even numbers of quarks, right? So if you add a 1/2 and a 1/2, you would get a 1. And the mesons basically are bosons that are just made up of 2 quarks. Now, I have a little star here on spin, if you're wondering what that is. That's actually because the graviton, even though we haven't detected it yet, if it exists, would have a spin of. And the guy that kind of pointed out how fermions behave is called Wolfgang Pauli here. And he basically said that identical fermions, so if you have 2 electrons or two quarks or whatever, the same. If you drain all the energy out of a system, say by cooling all these bosons, and they've done this in labs, you form what's called a Bose-Einstein condensate. All of the bosons can basically occupy the exact same state in the same space, and they look like they're just one object, okay? You can do this by laser cooling complex bosons, and they will look like they're just one thing. When you turn the lasers off, they heat up again and they become individual particles, and it's very weird, but it really does work that way. On the other hand, fermions don't. Fermions work like this, where you've got little energy levels, right? And if you try to put one in the lowest energy level, that's fine, as long as there's not another one there. If you try to put another one, it has to have the opposite spin, or else it can't go there. So in any energy level, all you can have is one with a positive 1/2 spin and one with a negative 1/2 spin. Those are the only two things you can fit in that level. So what happens is, as you add electrons into a system, you can have two at the first level, but then the next higher energy, you can only put two there. And then the next higher energy, you can put two. So basically, once you fill that in, you know, the next electron here has to go to this energy level. It can't go any lower, okay? And so that gives you this Fermi energy, is what they call it for fermions, and it gives you what's called a degenerate state or a degenerate gas. If you have a gas of electrons that's filled up all of its all of the lower energy levels, they call it degenerate, okay? Now this process of being degenerate actually causes an outward pressure, okay? And that pressure is what holds up a white dwarf. Okay, it's called electron degeneracy pressure, and it's basically as you push in on the electrons in this white dwarf, they basically resist being pushed together, and so that holds up the star. But the more you push, the smaller it can get, because those energy levels can get crammed together even more and more up to a point. And the point is when Chandrasekhar decided, he figured out that the electron degeneracy pressure can only hold up a stellar remnant up to about 1.44 times the mass of the sun. Okay, so if it's bigger than that, this won't help. It's still going to collapse and gravitation wins, okay? But if it's less than 1.44 times the mass of the sun, the electron degeneracy can hold it up. And so that's why we see these white dwarfs that go up to, you know, like the one that I showed you at the beginning was about 1.3 times the mass of the sun. Those can hold themselves up, but beyond that, you can't, okay? So remember I told you that neutrons and protons were 3 quarks. I'm just going to go into it a little more. Neutrons are 2 down quarks and an up quark, and protons are 2 up quarks and a down quark, okay? Now, if you have a neutron that's outside of a nucleus of an atom, they actually are very unstable, and within 15 minutes, it will decay to a proton plus an electron and a neutrino, okay? Now note that there's no electrons or neutrinos in a neutron for it to give off, but when this down quark turns into an up quark, it gives off a little bit of energy, and through Einstein's equation, E equals mc squared, that energy is related to mass, and it just happens to be related to the mass of an electron and a neutrino. And so when it deforms, that happens. Now the same thing happens in reverse. If you squish a proton and an electron together, you can get a neutron out, but it will absorb that electron and it still gives off a neutrino. So I'm not sure that makes a whole lot of sense mathematically, but it actually does if you look at the actual energy of each particle as it goes in. Okay, so each time it gives off a neutrino, that's why there's so many neutrinos out there, but this electron can be absorbed. And so in the case that star is bigger than 8 times the mass of the sun, when it stops fusing, like we said before, instead of just collapsing into a white dwarf, you're going to get a big explosion called a supernova. And the 2 results of that supernova are either it's big enough that it just falls right into a black hole at the core, or we get this extreme thing called a neutron star, okay? Now, neutron stars, basically what happens is as that core is collapsing, it gets to that limit for electron degeneracy pressure, and it says, nah, I'm just going to keep going. And it pushes all the electrons together so tight that most of them merge with protons, and you basically get a whole bunch of neutrons instead of the protons that were there. And so now you've got what we call a neutron star. Now, neutron stars are still held up by degeneracy pressure, but it's not electron degeneracy, it's neutron or some other quantum particle degeneracy, and that's part of what we need to figure out. But so far I've talked about a lot of densities, so I just want to compare them here and take a second before I go into what's in a neutron star and we get to the rest of that. So first of all, we talked about stars fusing hydrogen. In order for a star to fuse hydrogen, the density that you need is approximately the same density if you took a pound of butter and squeezed it into a single teaspoon. Okay, so if you could do that, and we can kind of do that on Earth, that's not that extreme, then you can get fusion to happen. Okay, but once the fusion stops, things collapse way more. And so for a white dwarf, you would take an M1 Abrams tank and crush it into that same teaspoon. That's when you get the pressure, the density that gives you that degeneracy pressure. Okay, so approximately, if you can squeeze a whole tank into a teaspoon, now that's getting pretty extreme. And that's something we can still maybe, in some of our best physics labs, still kind of explore, but it's not like an easy thing to do, right? Now, for neutron stars, on the other hand, the nucleus of an atom, if we could just take the nucleus by itself, make it big enough to fit in a teaspoon, it would weigh about 1,600 times the Empire State Building. So if you had 1,600 Empire State Buildings, squish them into a teaspoon, that's how much the nucleus of an atom would weigh. That's how dense they are. But in a neutron star, it's about twice as dense. Okay, so you get this about 3,200 Empire States per teaspoon of density. So way, way more than a tank, way, way more than even, twice as much as even just the nucleus is. So, it's very likely that things are getting squished there. Nucleuses can't stay intact, so you get separately neutrons, protons that are left, and that kind of stuff all mixed together, and we don't really know. So here's what we do kind of know, okay? Neutron stars have an atmosphere, okay? They're made of hydrogen, helium, and carbon, and they're about 2 centimeters thick, maybe 3. So they're super thin, just tiny atmospheres. Now, inside of that, we have the outer crust. That crust is mainly made of ions of different elements, and it's only about 100 meters thick. So it's thin also. And there's possibility that there's a little layer of iron on the outside, but for the most part, it's just really thin. It's crystalline, and so it's almost like a solid. Inside of that, we have the inner crust. And in the inner crust, we also have some ions, but we have in that what we call superfluid neutrons. Now, if you've ever heard of a superconductor, basically superfluid neutrons, neutrons can't conduct anything, but it's the same concept. They basically can move around within that superfluid without any resistance. So it's just like superconducting electrons, but we're talking about neutrons moving with no resistance, okay? And then a little bit left further in, we get to what's called the inner core, or the outer core, sorry. We're still in the outer core. So the outer core, basically same thing, but possibly protons. And if that's the case, they'd be superconducting protons, but instead of conducting the negative charge, they're conducting positive charge, and they're moving around there. And then finally, we get to the inner core, which we don't know actually what's there, and we're trying to figure that out. And to talk more about what that might be and how we figure that out, I'm going to let Sarah take over and finish up the talk for me.
So one possibility for the inner core, there's 3 neutrons. It's not even discharged, but the star has the name of neutron stars for a reason. But there's other possibilities. The truth is, we don't know what is in the inner core of neutron stars, so we don't even know if the name neutron stars is correct or not. And about those possibilities, we can have quarks, free quarks. So maybe the conditions in the inner core of neutron stars is so extreme is that the quarks that forms neutrons just became free quarks, and they is what they're in the center of neutron stars. There's other possibilities. One of them is that we have a particle called pions that is formed by an upper quark and an anti-down quark. And in this case, the core of the neutron stars would behave as a Bose-Einstein condensate. And another possibility is that there we have hyperons in the center of neutron stars. So hyperons, they are also baryons. So we can see here that hyperons are those particles here. And they also have free quarks. So an up quark, a down quark, a strange quark. Okay, they can have 2 strange quarks. The main difference about hyperons and, for example, neutrons is that we have 1 strange quark. And if you may remember the charge that we seen a few slides before, a strange quark is heavier. So hyperons are heavier than neutrons. And this is another possibility. We know what is inside? No. But there's a way of figuring out, like we have possibilities of trying to figure it out what is in there. And now I'm going to talk more about it. How can we discover what's in the side of neutron stars? So how can we test those models? And one way of doing this is measuring the mass and the radius of neutron stars. It's really hard to do. There's very few techniques that we can use to do that, but we are getting there. So first, I'm going to explain how can we use mass and radius to define what's in the core of neutron stars. And then I will talk about what are the observational techniques that we can use to do that. So like in this picture here, like this graphic, we have an equation of state. So we saw that an equation of state is something that relates density. So we have density here. It's energy density. So this is an energy divided by some volume. And here is pressure. And each one of those models is related to one theoretical possibility. So each one of those models that we talk about, and not only what is inside neutron stars, so we can have, for example, different models for hyperons, depending on how they behave, but each one of those models will generate an equation of state. And this equation of state can be what we call stiffer or softer. Basically, a stiffer equation of state would, like the neutron stars would behave like a wooden ball. So let's imagine that we have a neutron stars with not a big mass. Let's say a neutron stars with a mass equivalent to the sun. And they have a radii. So imagine that the same neutron stars, we put more mass. So we would have more pressure. But if it's a stiffer equation of state, the radius wouldn't change that much. So we'll try to squish it, but we cannot. And for a softer equation of state, it means if we put more pressure, then we would have a changing radius. So the main difference about a softer and a stiffer equation of state is that if we have more mass, we will have a smaller radius for a softer equation of state, but for a stiffer equation of state, the radius will not be that different. And one interesting thing is that we can use the equation of state to get what we call a mass-radius relationship. So those two graphics are related, and each one of those models will generate a new curve in here. And this curve will tell how the mass of neutron stars and the radius relates, and this we can test observationally. So here in this graphic, the two things that we can test, of course, is the format of the curve, but also the maximum mass that we expect for neutron stars. So we can measure mass of a few neutron stars in the sky. We can see which is the most massive one that we find, and this gives limits for this upper mass in here too. And this also can say what models are right, what are wrong, because, for example, those here have less than 2 solar masses, and we have neutron stars with with more than 2 solar masses found. So we know that those models are not right. So we can test the equation, the format of this curve, but also the maximum mass. And to talk a bit before, on how hard it is to get mass and radius of neutron stars, I will just do a little comeback to white dwarfs. And for white dwarfs, it's the same thing. We can relate the equation of state of white dwarfs with a curve of mass and radius. And this is for white dwarfs. Here we have different curves, but it's not different models. It just means that depending on the inner temperature that we have, like the temperature in the core of the white dwarf, we'll have a different equation of state and then a slightly different curve. But the one thing I want to show you here is those points. So those points here are all observations of white dwarfs. It's mass and radius of white dwarf that we have measured with a survey called SDSS. And we can see that we have several of them, tons. Probably there's hundreds or even thousands of white dwarfs in here. So it's really easy to measure. But it's not true for neutron stars. So we don't know the equation of state, and it's really hard to get those observational points. But we are getting there. There's a few techniques, and those are the techniques that I want to talk about right now. And we talked about it before, but I just wanted to remember before we continue why it's so hard to measure the neutron star radii and also its mass. and mostly because it's hard to see like its surface. To measure the radius, you basically need to get some information about the geometry, the surface. So how can we do that, like, if they are so tiny? So this is a comparison. Here we have Earth, and here is like a size of an average white dwarf. So an average white dwarf will have the size of the Earth, and this would be a neutron star. So it's really smaller, much harder to see. So I'm saying this, it's hard to see neutron stars, but we do have neutron stars that we know. Like, if you look in the internet, we see that even just in the Milky Way, we know a few thousands neutron stars. So how it's hard to see them if we know a few thousands of them? So I'll just start saying that this is like an artistic vision. It's not what we see, but I wanted to show you, because in this upper part here, we have a pulsar, and here it's a X-ray binary. So for the star, a pulsar, what we will see, like, it's this structure in here. So we don't see the surface of the neutron star, just this structure that is emitting in other wavelengths. So we'll see it in radio, maybe in X-rays, so in higher energies, but not the photosphere. So we cannot see this surface of the neutron star, just this part. And here's an X-ray binary, so it's a system with two stars. So the neutron star is in here. But here is another star. It can be a star like the sun. When what happens is that because the gravitational potential well of the neutron star is so high, that mass of these other stars just fall into the neutron stars. So it will form this disk of mass that is falling to the neutron stars, and then some jets. And what we see when we are observing those systems, we will see the disk, we can see this jet, we can see this other star, but not the neutron star. So we see everything in the surroundings, but not the neutron star specifically. And how can I get information about mass and radius of neutron stars simultaneously? And I say this because it's slightly easier to get mass, but radii is really difficult. And one way of doing this is with gravitational wave. So we have almost 100 events of gravitational wave detected up to this date, but only 2 of them are important for this presentation. 170817 and 190425. This is because those were the only 2 events that were 2 neutron stars merging. So gravitational waves happens, we observe them when we have a neutron stars and a neutron stars and a black hole, or 2 black holes. And most of them are with 2 black holes, at least like the ones that we detect right now. So there's more video in here. And like, we have 2 neutron stars, and what happens is that they come closer and closer and closer. They will emit gravitational wave when they are merging. And depending on their masses, the difference of masses, and also what object will form after this merge, we can have also this immense amount of light being emitted. So this is some gravitational wave events that we have fine-tuned right now. And the one that has 2 neutron stars is this one, 170817. And it's here just to say that we can discover first that are 2 neutron stars and also their masses, studying the frequency and also the amplitude of the waves that are being observed. And from neutron stars specifically, those events not only give us the information about the masses of the 2 neutron stars, but also about the radii. Depending on the radii, if it's larger or smaller, we'll have different tidal effects during the merger that will affect this wave that we are seeing. So this will also affect the gravitational wave, and we can get estimates for the mass and the radii from those events. And not only that, because specifically for this event here, 170817, we have the gravitational wave, and then we have light being emitted afterwards. So we had electromagnetic counterparts in gamma rays and other wavelengths. So we had a light that we could observe afterwards. And there's a reason for that. So of the 2 events, this one, which is the second one, 190425, probably follow into this path here, that after the merger of the 2 neutron stars, we formed a black hole. So we didn't have a third neutron stars being in the system. So like the two initial ones and the last one, no, this is a black hole. It is possible to have light, but it doesn't happen in that case. But what can happen is that if those two neutron stars are not that massive, when they merge together, they will still have room to be a new neutron stars. And this is what happens in this path. Like this part here is a neutron stars right after the merger, and it can become a black hole pretty fast or continue to be a neutron stars, and then after more time, so here it's like after 1 second, and here would be after a day, we can have a neutron star or not. So 170817 followed this path. We don't know if it became a neutron star, for example, after a day, but it was sure that we had a neutron star at least for some time. And we could get information about this too, because in this event, we had the two neutron stars in the beginning and this one in the end. And this one in the end gave us, among other informations, one information that was pretty interesting is that the maximum mass of a neutron star has to be something close to 2.18 solar masses, 2.16, 2.18 solar masses. And we got this from this aftermath, this light that was emitted after the gravitational waves. So this event was pretty rich. It gave us information about the mass and the radii, but also what happened afterwards. And the second way of measuring mass and radius of neutron stars simultaneously come from this telescope here, NICER. And it's in the International Space Station, so the telescope is not this whole thing. This is the International Space Station, and the telescope is just like this small box in here. And what the telescope does is get the information from X-rays. So they get what we call light curve, which is this. And they studied, up to this date, two neutron stars, this one and this one. And the one thing that makes this telescope stand out related to other telescopes and X-rays that we have, because we have a few, is that it has a very high timing resolution. So it can take information from the neutron stars 1,000 times per second. And this is really, really important because those stars, they rotate pretty fast. So we can see here, for example, that this star rotates 346 times per second, so rotates surrounding its own spin. So it's like Earth takes 24 hours to do one rotation, and they do 346 in 1 second. And this one, it's 205. So we really need this high timing resolution, and this telescope is the best one to do that. But how can we get information from mass and radii from that graphic? And before explaining that for neutron stars, I just want to come back a bit to Eclipse. So here is like a normal sun. It can be the Earth. And here's a planet that passes in front of the sun. And we see that when the planet passes in front of the sun, it kind of blacks out a bit of the light of the sun. So we have a small eclipse of the light that is being emitted by the star. And this is how we detect exoplanets. We have other techniques, but this is one of the most effective ones. And what we do is just observe if we see this sudden drop in light that comes from the star. And the idea is pretty similar. So what happens here is that this is a neutron star, and it's rotating. And we see that we have those weird shapes, spots in here. And those spots are those structures that I've showed before that emit in higher energies. So, but they are connected to the surface of the neutron star, so they rotate with the neutron stars. And when they do that, what happens is that at some points, those structures are eclipsed by the neutron stars, and at some point they are not. And this is what generates this curve that has this sinusoidal shape, because at some points, the structure is eclipsed, and some points it's not. And we can get information from radios, mostly because of the geometry. So depending on the size of the this spot, and also when they are located, and the radius of the neutron stars, this curve will have a different shape. And we can get information from radii, testing several possibilities of radius and spots, and seeing which one fits. And we can also get information from mass, and this comes from general relativity. So here, there's one picture, like one small video that shows that. So what happens is that depending on the mass, and here they say that bigger masses has smaller radii, light bends in a different way. So when light bends in a different way, because of general relativity, gravity bends light, we see the light that is like being emitted by the star in a different way, and this also changes the shape of the curve. And we have another video to show that, slightly better. So here, like, we have two stars, and one of them has no gravity, and the other one has a strong gravity, and we see the effect of general relativity in here. So we see that, like, the shape of the curve changes, and here is like there's a different shape for the same size of spot just because gravity is different. So gravity also changes the shape of that curve that we saw. And what astronomers, scientists do is testing several different masses, several different radii, and coming closer to the value that is the real one for that star. Of course, it can be something, when I say this, it can sometimes appear that is something that can have some room for error, but actually it's pretty precise. And to confirm that, what they do is that there's two different teams in the world that analyze this data, and they have programs that were done separated, and they don't talk to each other when they are analyzing data. And when they finish, they compare the results, and the results are always pretty close. It's really hard to do. It requires a lot of computation, a lot of time, a lot of effort, but it's possible. And those are the results that we have for those two stars right now. So we see that it's not a small point like we have in a white dwarf. It's actually a region that it's possible that the mass and the radius are, so the error bars are much higher. But those are the possibilities of values for mass and radius, the region for these stars and the region for this one. And we see that we cannot rule out a lot of models yet, but we are getting there. For example, this model here, that's actually a model that includes a nucleonic, so it's with a neutron. It's not possible. We also see that quark models are like close to the outer regions of those two curves, so they are less likely than the other ones in here. But we can have, for example, hybrid models. Hybrid models is models that has, for example, neutron stars and quarks working together in the core. So it's not just quarks or not just neutron stars, but both of them. We can have hyperons. So we are not completely sure yet, but we are getting there, and we see that with those informations, we are starting to ruling out a few possibilities. And in my last slide, I'm just going to show this picture that kind of joins all information that we have. So like this information here come from gravitational waves, and those here from the NICER telescope I showed you. And we see that when we put all of them together, we probably have seen like a stiff equation of state. And we can remember that if it's stiffer, we can change the mass, and the radius doesn't change that much. Here it's in diameters, but in the radius, we just divided by 2. Diameters is 2 times the radii, so we see that. And here also shows a good estimate for the radius of a neutron stars. Before that, we didn't know, we didn't have an idea. Like for models, we would say that it's something between 10 and 15 kilometers, but it's a lot. It may seem not that much, but it's 50% error. And now we are kind of sure that neutron stars have a radii that is close to 12.513 kilometers. So we narrow it down. We know that this is probably the radius of a neutron stars, and also that we are seeing an equation of state, so a model that doesn't change that much the radii with the mass. And this seems to rule out, for example, quark models. We are sure of that? Not yet, but it's possible. It's more likely that it's not quark model than other things. And one interesting thing about this topic, and this is how I want to finish this presentation, is saying that we are not sure what is inside of neutron stars. So here we are like talking to you about the real science that is being done at this very moment. So we maybe 5 years from now we'll have an answer for it. We'll have more gravitational wave detections. This telescope will continue to work, and we probably will have a better answer for that. But for now, what we can say is that we are working on it. Those are the models that scientists have. And with that, I really hope that we have enjoyed and learned something from it. And maybe in, I don't know, 5 years from now, we can have another talk about it. And then we will say, oh, that talk that we did some time ago, now we have an answer for that. So thank you for your interest in this topic. And if you have any questions, we both will be really happy to answer. And we'll have next talk will be May 7th, and will be about Voyager. So if you are interested, especially in this case, in aerospace engineering and okay. So if you're interested, you can. I don't know why it's not working that talk. Okay. So if you're interested in Voyager, you can come here and make stuff. Any questions? Anything that may interest you to know further? Yes?
What's the likelihood of a star turning into a white dwarf or a neutron star or something else?
So when we have a star like the sun, it will evolve at some, it will continue to evolve. And it can become a white dwarf, neutron stars, a black hole, and what defines what will become one or the other is the mass of like the star. So for example, sun has a very low mass. It's not a massive star, so it will become a white dwarf for sure. If it's a star that has roughly, this can change a bit, but it's 8 solar masses, then less than 8 solar masses will become a white dwarf. More than that will become a neutron star. Now to become a black hole, the star has to have something greater than 25 solar masses. So a star that is 25 more massive than the sun, so it's really massive, will become a black hole. And a neutron star is between 8 and 25, so it's in the middle.
Thank you.
No problem.
Just kind of a follow-up question.
Yes.
Like in the galaxy, whether it's the Milky Way or Andromeda, what is the percentage of the white dwarfs versus black holes versus neutron stars?
So most, okay, there's two questions here. There's two things I can say. So one thing is that we have the stars like the sun that we call main sequence, and most of them are not that massive. So I'd say 99%, 95% of them will become white dwarfs. But there's another thing in this question. So in the end, most stars will become white dwarfs in the end. Not neutron stars, not black holes. But there's another thing. So those stars that are less massive like the sun, they tend to live for a longer time. So for example, our sun will live for like 8-10 billion years. And like in the main sequence, and then it will have a giant phase, so it will live a bit more than that. But we'll live for some time. And stars that are really massive, so that has like 20-something solar masses, will just live for a few million years, so 500 million years, let's say this number, but it can change depending on the mass. So what happens is that they last very little. So we have to take those two things into account, because in one point, we will have more stars that will become white dwarfs, but those will become white dwarfs. They'll take more time to become a white dwarf. But neutron stars, from the time that the star is born until the time that they become a neutron star is pretty fast in astronomical times. So in our galaxy, it seems that the estimate is that there's probably a lot of millions, maybe close to 1 billion neutron stars. So it's a lot, but we don't see them because they faint really quickly. So we just know a few thousands because we cannot see them. At some point, they just become like small balls in the sky that no one can see.
Thank you.
No problem. Any other questions?
All right. Well, thanks for coming, and hope you enjoyed it. And we will see you next time, hopefully on May 7th for the Voyagers.